There is a version of this story where you read the changelog, nod along, and move on. This is not that version. OpenClaw, the 8th of April, 2026 dropped today, and beneath what could easily be written off as a routine update is a release that genuinely changes how the system works in ways that operators, developers, and anyone running agents at scale are going to feel immediately. Welcome to OpenClaw Daily. I'm Nova.
And I'm Alloy, and this is OpenClaw Daily. Today is April 8, 2026, and we have a genuinely substantial episode ahead. The OpenClaw April 8, 2026 release is our anchor story, and we are going to do it properly, because it deserves it. There is a new inference CLI that changes how you interact with models, a media generation fallback system that eliminates an entire class of failures, a sessions UI that finally gives operators real control over context compaction, and the complete restoration of the memory and wiki stack that a lot of people have been waiting for. Then we are going to talk about Project Glasswing, Anthropic's newly announced coalition with Amazon, Apple, Microsoft, Nvidia, and a roster that reads like a who's who of critical infrastructure, all organized around a frontier model that finds zero-day vulnerabilities at a pace that actual human security researchers cannot match. We will look at MegaTrain, which figured out how to train a 100 billion parameter model on a single GPU. We will talk about evidence that your AI writing tool might just be a Claude clone in a cheap disguise. And we will close with something genuinely fun, an LLM that learned to play a shoot 'em up on a 1970s 8-bit computer using nothing but text descriptions of the game state. Nova, let us start with the release, because there is a lot to get through.
There really is, and I want to set the context properly before we dive in, because I think there is a tendency to skim changelogs, and that would be a mistake here. OpenClaw has been building toward something for a while, and this release feels like the point where a bunch of different subsystems that have been developing somewhat independently finally snap together into a coherent whole. We are going to go through the major additions one by one and talk about what they actually mean in practice, not just what they do. The first and probably most significant addition is the new Infer Hub CLI. The command is OpenClaw Infer Hub, and it is being described as a first-class interface for provider-backed inference across model tasks, media generation, web search, and embeddings. Let me translate that into what it actually means for you in practice. If you have been working with OpenClaw for a while, you have probably accumulated a set of workflows where you are using different providers for different tasks. Maybe you use one model for code generation and another for creative writing. Maybe you use one provider for image generation and another for speech. The challenge has always been that each of those providers has its own authentication setup, its own rate limits, its own way of handling errors, and its own configuration. Managing all of that across multiple providers in a single agent workflow was genuinely painful. People were writing wrapper scripts, maintaining multiple config files, and building their own fallback logic. What the Infer Hub does is it becomes that unified layer. You describe what you want: a model task, a media generation job, a web search, an embedding, and the hub routes it to the right provider, handles the authentication, handles error conditions, and returns a structured result. If one provider is down or rate limited, it routes to your configured fallback. If you need to switch providers for cost reasons or capability reasons, you configure that at the hub level and the rest of your workflow stays the same. It is the difference between managing a collection of point solutions and having an inference abstraction layer that you can actually reason about.
And the Infer Hub is not just routing requests, it is doing intelligent routing. It understands provider capabilities, it can remap parameters to what a given provider actually supports, and it preserves your intent across provider switches. If you ask for a vertical video and your primary provider only supports horizontal, the hub will find a provider that supports vertical and adjust the request appropriately. That sounds like a small thing, but it eliminates an entire category of frustrating failures where the request is technically correct but the provider just cannot do it.
The second major addition, which is related and builds on the same philosophy, is the media generation auto-fallback system. This applies to image, music, and video generation. If you have multiple auth-backed providers configured for any of these modalities, OpenClaw will now automatically route to the next available provider if your first choice is down, rate limited, or does not support the specific capability you requested. Let me give you a concrete example of why this matters in practice. Say you have an agent workflow that generates images. You have provider A configured as your primary. Provider A goes down for maintenance, or hits a rate limit, or you request a size or aspect ratio that provider A does not support. Previously, the workflow would fail or return an error and someone would have to manually intervene, reconfigure, or wait. With the auto-fallback system, OpenClaw detects that provider A cannot fulfill the request, finds provider B in your configuration, adjusts the parameters to what provider B supports, and completes the request without intervention. You get the result you wanted without knowing that anything switched in the background.
That is the kind of reliability improvement that compounds across a large number of automated workflows. One failed image generation request might be a minor inconvenience. 1,000 of them per day across a production agent fleet is a serious operational problem. Auto-fallback at the system level means you do not have to build this logic into every individual workflow. It is handled once at the platform layer, and every agent and workflow benefits immediately.
And the fallback system is not just binary failover. It is intelligent parameter remapping. Different providers support different capabilities, different size constraints, different formats. The hub understands those constraints and translates your request into something the available provider can actually fulfill. So if you request a 60-second video and your primary only supports up to 30 seconds, it will find a provider that can do 60 seconds and route there. If you request a specific aspect ratio and the fallback provider uses different terminology for its capabilities, it maps that correctly. The goal is that the request you make is the request that gets fulfilled, not a degraded version that happens to fit the constraints of whoever is available. The third major addition I want to focus on is the sessions UI branch and restore functionality. This one matters enormously to anyone who runs long agent sessions, and the people who have been asking for it have been asking for a while. Here is the problem it solves. When you run an agent session for an extended period of time, OpenClaw performs context compaction. It compresses and summarizes the conversation history to keep context usage manageable. That process is necessary, but it has a cost. You lose some of the granularity of the original conversation. If the compaction algorithm summarized something incorrectly, or if you realize 3 hours into a session that you needed something from an earlier context that got compacted away, you had no recourse. You could not go back. The summarization was lossy and irreversible. What the new branch and restore system does is it creates persisted checkpoints before compaction happens. The system snapshots the session state at a known good point, and operators can use the session's UI to inspect those checkpoints and roll back to a pre-compaction state if needed. It is the difference between editing a document with autosave and editing one where every save overwrites the previous version. You now have version history for your session context.
And the restoration is not just a rollback, it is a proper restoration that you can branch from. You can restore to a prior state and continue from there, or you can use that checkpoint as a branch point to explore a different direction without losing the original thread. For operators running complex agent workflows where you might want to explore alternative approaches without committing to them, this is a genuine capability improvement.
The fourth major addition is the restoration of the memory and wiki stack. This has been in and out of the codebase for a while. There were versions of it that were incomplete or had missing components, and it is now fully restored with the full feature set. Let me go through what that actually means. The memory and wiki stack is OpenClaw's system for persistent agent memory. It is the difference between an agent that starts each conversation fresh with no knowledge of prior interactions, and an agent that has a long-term memory that it can query, update, and reason about. The stack includes a plugin, a CLI, sync and query and apply tooling, memory host integration, structured claim and evidence fields, compiled digest retrieval, claim health linting, contradiction clustering, staleness dashboards, and freshness-weighted search. Let me unpack a few of those because they each represent a real capability. Structured claim and evidence fields means that when the agent stores a memory, it can tag it with claims, factual assertions, and the evidence that supports those claims. That makes the memory system not just a storage layer but a knowledge graph. You can ask questions like what do I know about X and what is the evidence for it? Claim health linting then validates that the claims in your memory are internally consistent, and contradiction clustering groups claims that conflict with each other so you can surface and resolve inconsistencies. Staleness dashboards and freshness-weighted search mean that when you query the memory system, results are ranked not just by relevance but by how current they are. Older memories that might be outdated are flagged appropriately, and the system bias toward more recent information in its responses. For agents that operate in environments where information changes frequently, that is important.
And the restoration of the full stack means that all of these components work together as an integrated system rather than as partial implementations that required workarounds. If you have been running OpenClaw as an agent memory system and working around missing pieces, this release is worth retesting your workflow against the native implementation. The gap between the workaround and the native system was probably significant.
The fifth major addition is the new webhook ingress plugin. This is a smaller addition in terms of code footprint, but it addresses a real gap that a lot of operators have been working around manually. External automation systems, CI pipelines, monitoring tools, scheduled jobs, webhooks from third-party services have always had a challenge integrating with OpenClaw workflows. You could trigger them, but the integration was typically fragile or required custom code. The webhook ingress plugin adds per-route shared secret endpoints to OpenClaw. External systems can now authenticate with a shared secret and trigger bound task flows directly. That means your CI pipeline can call a webhook, authenticate securely, and trigger a specific OpenClaw workflow without you having to build a custom integration layer. The plugin handles the routing, the authentication, and the workflow binding. For organizations that are integrating OpenClaw into existing automation infrastructure, this removes a meaningful source of complexity. The sixth addition is the pluggable compaction provider registry. Compaction, the process of summarizing and compressing long conversation histories to stay within context limits, has traditionally used the built-in LLM summarization pipeline. This change lets you replace that with a different model or service entirely, configured via agents.defaults.compaction.provider. The practical implication is that if you want your compaction to be handled by a faster, cheaper model that does not need the full context of your conversation, you can configure that now. The system falls back to the built-in LLM summarization if the configured provider fails, so you do not lose reliability. But for production deployments where you are running thousands of sessions and compaction is happening constantly, being able to route that to a model optimized for the task rather than the most capable model you have can matter a lot for cost and latency.
And the system prompt override feature is worth a mention too. Agents.defaults.system prompt override lets operators run controlled prompt experiments without modifying the base configuration permanently. You can test different system prompts against the same agent configuration and compare results. The heartbeat prompt controls are related. They let you keep heartbeat runtime behavior enabled for the useful purpose of maintaining session awareness without injecting the full heartbeat instruction set into every single turn. That keeps the actual prompts cleaner and more focused, which matters for token usage and for the quality of the model's responses.
Let me do a quick run-through of the other notable additions and changes, because there are several that matter in specific contexts. Google Gemma 4 is now supported natively. More importantly, the Google fallback resolution is fixed. Native Google Gemma routes work correctly again, which apparently they were not fully doing in a prior version. If you have been using Gemma 4 and seeing unexpected routing behavior, test it against this release. The Gemma thinking semantics are also preserved. If you want to use Gemma 4 with thinking disabled with explicit thinking off semantics, that works correctly in compatibility wrappers. So you get the reasoning capability when you want it and you can disable it when you do not. Claude CLI is restored as the preferred local Anthropic path. This affects onboarding, model authentication guidance, Docker flows, and Docker Claude CLI live lanes. If you run Anthropic models locally without going through the API, this is the path the system will recommend and support by default. Ollama Vision models now accept image attachments natively. The vision capability is detected from the API show response, and the system sets image input automatically on models that support it. No workarounds required, just attach the image and it works. The memory and dreaming system now ingests redacted session transcripts into the dreaming corpus with per day session corpus notes, cursor checkpointing, and promotion and doctor support. If you use the Dreaming system for creative or investigative work, the addition of redacted session transcript ingestion means your Dreaming corpus can incorporate a broader range of your actual session activity. On the provider side, there is a new bundled RC AI provider plugin with Trinity catalog entries and OpenRouter support. RC is a relatively newer entrant in the provider space, and this plugin makes it a first-class supported provider in OpenClaw. The context engine changes are more internal but significant for plugin developers. Available tools and citations mode are now passed into the assemble function, and memory artifact and memory prompt seams are exposed to companion plugins. What that means in practice is that plugin authors can now build integrations that consume active memory state without having to reach into OpenClaw internals in ways that break across versions. It is a better extension API. And there is a meaningful batch of fixes that are worth knowing about even if they do not affect you directly. Telegram setup is fixed. It now loads contracts through packaged top-level sidecars, which resolves the import errors that were happening during gateway startup for installed NPM builds. The same fix applies across all bundled channels: Blue Bubbles, Facetune, Google Chat, IRC, Matrix, Mattermost, Microsoft Teams, Nextcloud Talk, Slack, and Zalo. Slack proxy support is now working correctly. Ambient HTTP and HTTPS proxy settings are honored for socket mode WebSocket connections, including NO_proxy exclusions. If you have been running Slack behind a proxy and seeing connection issues, this likely resolves them. The host exec and environment sanitization changes are security relevant. Dangerous overrides for Java, Rust, Cargo, GIT, Kubernetes, Cloud Credentials, Config Paths, and Helm are now blocked at the environment sanitization level. This prevents host-run tools from being redirected to attacker-chosen code, credentials, or repository state. This is the kind of fix that you hope you never need but are very glad is there. The allowList command now requires owner authorization before changes are applied, which prevents non-owner but command-authorized users from persistently rewriting allowList policy. Auth for OpenAI Codex OAuth has been improved with fresh credential reload inside the locked refresh path, which should stop the stuck religion problem that occurred after token reuse. And the Discord event creation has been upgraded. Event create now accepts cover image URLs or local file paths, validates PNG, JPG, and GIF media, and passes the encoded payload through Discord admin action and runtime paths. You can now create Discord events with proper cover art programmatically. That is a lot. The full changelog is available at github.com/openclaw/releases, and I would encourage you to go read it, because there are details in the actual PR citations that we do not have time to get to. But those are the headlines. Let us move to story 2. Anthropic announced Project Glasswing today, and I want to start with the announcement itself and then get into the questions it raises, because it is one of those announcements that is simultaneously impressive and a little unsettling. The coalition Anthropic assembled is remarkable in its scope. Amazon, Apple, Broadcom, Cisco, CrowdStrike, Google, JP Morgan Chase, Microsoft, Nvidia, Palo Alto Networks. This is not a list of AI startups or research institutions. This is a list of the companies that collectively represent the infrastructure, financial system, and security posture of the global internet. When Anthropic puts out a press release and that is the partner list, the ambition of what they are describing is different from what we normally see in AI safety or security announcements.
The press release framing is collective defense. The language is about collaboration, shared mission, and applying AI to the problem of AI-generated vulnerabilities at scale. And I think the intent is real, the resources being committed are real, the participating security teams are real, and the problem they are describing is real. But I also think it is worth being precise about what the structural arrangement actually is before we accept the framing at face value.
The centerpiece is a model called Claude Mythos Preview. Anthropic describes it as a frontier model positioned specifically for offensive security research. It is not publicly available. It is not open source. Access is controlled by Anthropic and provided to the coalition partners under terms they have negotiated. The capability numbers are genuinely striking. Mythos Preview scored 83.1% on the CyberGym benchmark. That is a security evaluation benchmark. For reference, Anthropic's own Opus 4.6, their previous top-of-the-line model, scored 66.6%. The gap between the two is not small. This is a specialized, unreleased model that outperforms the best publicly available model by a very significant margin on the exact task they are deploying it for. And the results they have produced are not cherry-picked. They say the model found thousands of zero-day vulnerabilities during testing. Thousands. In existing, actively maintained codebases. Among the specific findings they cited, a vulnerability in OpenBSD that has been present since 1998, 27 years, and a flaw in FMPEG that has been sitting in that project for 16 years. These are not easy finds. These are vulnerabilities that have survived decades of code review, security auditing, and normal development cycles. The model found them in the course of automated scanning.
And it found them fast, presumably. They do not give specific timelines, but the implication is that this was done in a research evaluation period, not over years of manual effort. A 27-year-old bug in a widely used open-source operating system, found by a model reading code. That is the capability level we are talking about.
Anthropic is backing the coalition with real resources. $100 million in compute credits for security research, and $4 million in direct funding to open-source security organizations. That is not a symbolic commitment, that is real money that will fund actual security research work.
But here is the question I keep coming back to. What does coalition mean when one party controls the weapon? Mythos Preview is not open. It is not publicly available. The partners get access under terms that Anthropic sets. Anthropic decides who can use it, for what, and under what conditions. So what we are actually seeing is a group of very powerful organizations becoming dependent on Anthropic's API for their security research posture. That is a different structural relationship than a genuine multilateral coalition where everyone has equal access and equal voice.
And that matters for a few reasons. The first is leverage. If a significant portion of global critical infrastructure security research is running through Anthropic's model, that is an extraordinary position. JP Chase, Apple, Amazon, these are organizations whose security posture has material impact on global financial systems and supply chains. When Anthropic sets terms for that relationship, they are sitting across the table from some of the most powerful institutions in the world, and those institutions have already invested in building workflows and institutional knowledge around the model. That is a deep relationship that is not trivial to walk away from. The second question is what happens when the model finds something in a partner's code. Not a competitor's code, a partner's code. OpenBSD and FMPEG are the examples Anthropic cited for what the model can find. But what about when it finds something in Google's code, or Microsoft's code, or JP Morgan's code? What is the disclosure timeline? Who controls that? Is there a window before the partner is notified? Is the disclosure automatic? These are not academic questions. The answers to those questions determine whether this is a genuine security coalition or a security intelligence relationship.
And the third question is what this means for the broader security ecosystem. If the dominant model for security research is a proprietary Anthropic model that only coalition partners have access to, what happens to the open-source security tooling ecosystem? Researchers who do not have access to Mythos Preview are working with significantly less capable tools. The gap between what Anthropic's partners can find and what everyone else can find widens. That has implications for the overall security of the Internet that go beyond the coalition itself.
I want to be clear that I am not saying the announcement is bad or that the intent is wrong. I think the problem they are describing is real. I think AI-generated vulnerabilities at scale is a legitimate and growing concern. I think the capability they are demonstrating is remarkable. And I think having actual security practitioners from CrowdStrike, Palo Alto Networks, and Cisco involved in the feedback loop probably makes the model meaningfully better than it would be otherwise. The cooperation is real on some level. But the structural arrangement, one company controls the weapon, Everyone else shows up as a customer or a partner on terms that company sets is not the same thing as collective defense. And I think it is worth being clear about the difference, because the framing of coalition is doing a lot of work in the announcement that the actual arrangement might not fully support.
You can read the full announcement at anthropic.com/glasswing. It is worth reading the actual text and forming your own view rather than taking the headline framing at face value.
Let us move to story 3. There is a new paper on R14 called MegaTrain, and I want to just state the core claim before we unpack it. MegaTrain can train models with over 100 billion parameters on a single GPU. One GPU. Not a cluster. Not a specialized machine. One GPU.
I want to make sure people understand why that sounds impossible and then understand why it is actually working. The traditional constraint on training large models has been VRAM. GPU memory holds the model weights, the optimizer state, the gradients, and the activations for each training step. At 100 billion parameters, the numbers are staggering. Even with 16-bit precision, you are talking about 200 gigabytes just for the weights. The optimizer state for a 100 billion parameter model trained with Atom is roughly 3 times the model size, 600 gigabytes. No current GPU has that much VRAM. The standard solution is model parallelism: shard the model across multiple GPUs, pipeline the computation, and accept the communication overhead.
MegaTrain takes a different approach. Instead of distributing the model across GPUs, it keeps the model weights and optimizer state in host CPU memory and treats the GPUs as disposable compute units. When a GPU needs to do a piece of computation, it streams the relevant weights from CPU memory, performs the arithmetic, and streams the results back. The GPU is not storing the model, it is just doing the math on data it fetches on demand.
And the reason this is becoming viable now is that GPU compute density has been advancing faster than GPU memory capacity. Bandwidth between CPU and GPU has been improving significantly with newer architectures like the GH200, which combines CPU and GPU memory in a unified pool. The H200 has 1.5 terabytes of CPU memory available for the system, and the bandwidth between CPU and GPU on that platform is high enough that streaming weights in and out is not as punishing as it would have been on older hardware.
They demonstrate training a 120 billion parameter model on a single H200 with 1.5 terabytes of system RAM. That is a lot of RAM and it is not cheap, but a single H200 is a commercially available machine. You do not need a data center. You do not need a cluster. You need one very expensive server. And that is a meaningful change in the accessibility of frontier training.
For smaller models, the numbers are actually impressive in terms of throughput. MegaTrain achieves 1.84 times faster training than DeepSpeed 0-3 on a 14 billion parameter model. 0-3 is one of the most widely used approaches for distributed training of large models. Beating it by nearly 2x on a single machine on a smaller scale model suggests the streaming architecture has genuine efficiency advantages, not just memory advantages.
But the number that I keep thinking about is the 7 billion parameter model trained with 512,000 tokens of context on a single GH200. 512,000 tokens. That is a frontier-scale context window. Gemini 1.5 Pro launched with a 1 million token context window and it was considered a landmark achievement. MegaTrain is demonstrating that you can train a model with 500,000 tokens of context on one chip. One GH200. No cluster. No InfiniBand networking. No special interconnect. One chip.
The implication is a significant democratization of frontier research capability. A university lab, an independent researcher, a small company, they can now run experiments that previously required a cluster of H100s. The cost curve for this kind of training is changing. It is not free, and it is not trivial, but the gap between what you can do on a research budget and what you can do at a major lab is getting meaningfully smaller.
And it has implications for the concentration of AI capability more broadly. If training large models becomes cheap enough to do on-premise without specialized infrastructure, the moat that large labs have is not gone, but it shrinks. The advantage shifts from you have access to training infrastructure nobody else can afford to you have access to more training infrastructure than anyone else. Those are different competitive positions. The paper is at arXiv.org/abs/2604.05091. The technical details of how they manage weight streaming, gradient computation across the CPU-GPU boundary, and optimizer state management are non-trivial and worth reading if you are working in this space. Story 4. A fingerprinting study of 178 AI models turned up something that has been sitting in the back of my mind since I first saw it. The researchers found 9 distinct clone clusters, groups of models that showed over 90% style similarity to each other despite being trained completely independently. Not similar content. Identical style fingerprints. 9 separate groups of models that arrived at the same writing style through independent training runs.
The headliner is Gemini 2.5 Flash Lite, which is Google's budget model, the lightweight, low-cost version of their flagship. According to the study, Gemini 2.5 Flash Lite writes with 78% style similarity to Claude 3 Opus. And it is 185 times cheaper to run. Let me just sit with that number. 185 times cheaper. You can get a model that writes in a way that is 78% similar to the best thing Anthropic makes, at a fraction of the cost, from Google.
The 2 explanations the researchers propose are both probably true to some degree, and they lead to very different conclusions. Explanation 1 is model convergence. Given enough scale and similar training approaches, independent training runs naturally fall into the same patterns. Everyone is using similar pre-training data, the same books, the same code, the same articles. Everyone is using similar human feedback signals, the same preference datasets, the same raters, the same notion of what good writing looks like. If everyone is optimizing toward the same target, they eventually arrive at the same basin of attraction, even from completely different starting points. The style that humans consistently rate as helpful and trustworthy might just be narrower than the field realized. Explanation 2 is that Claude's style is a strong RLHF attractor. Claude's conversational DNA, balanced, thoughtful, appropriately hedged, readable, structured, is not an accident. It is the result of very deliberate, very expensive training by Anthropic. And if that specific style is what humans consistently rate as helpful and trustworthy, then every other model that wants high user satisfaction scores will be pulled toward it. Not because they are copying Claude, but because they are all discovering the same optimal response pattern, and Claude got there first and had the brand recognition to make it feel like Claude's voice was a unique identity rather than a statistical attractor.
I think the second explanation is probably more correct, and it has a specific implication that I want to be direct about. If the personality that AI labs spend months engineering is actually a strong RLHF attractor, then it is not a moat. It is a magnet. And once you are a strong enough attractor, everyone else gets pulled toward you whether they want to be or not. Their models converge to your style even if they never trained on your outputs.
And if that is true, then any startup that is building a product and claiming their AI has a unique, differentiated voice is probably building on a foundation that is thinner than they think. If the underlying models are all converging to the same style regardless of how they were trained, then your unique AI personality is probably just a prompt template. And a prompt template is not a durable competitive advantage. The discussion thread is live on Hacker News, item 47690415. Go read it. There are some genuinely interesting takes in there from people who have thought about this from both the model development side and the product side. Story 5. A developer connected GPT-4o to a Commander X16 emulator. For those who do not know, the Commander X16 is an 8-bit home computer designed as an open-source recreation of the Commodore 64 experience. It uses a 6502 processor, the same chip family as the original C64. It runs at 8 MHz. It has 128 kilobytes of RAM. By any modern standard, it is an artifact. The setup for this experiment was deliberately minimal. No pixel data. No audio. GPT-4o received only structured text summaries of the game state, player position, enemy positions, bullets on screen, score, lives remaining, whatever the emulator could export as plain text. The model had to play a shoot-'em-up game using nothing but words.
And it worked better than you would expect. The model developed strategies over time. More interestingly, it started keeping its own notes on enemy patterns, not because anyone told it to keep notes, but because it recognized that tracking observations across turns was useful and figured out a way to do that within the constraints of the text interface. That is emergent metacognition. The model recognized a need for persistent state across interactions and invented a notational system to satisfy that need without being asked.
Eventually, it found an exploit in the Commander X16's built-in AI opponent, a behavior that the original game developers had not anticipated. It was not just reacting frame by frame to what it saw. It had built a model of how the AI worked, identified a weakness in that model, and exploited it. The developer did not expect that. The model just noticed.
The interesting part is not that an LLM can play a video game. We have seen that. The interesting part is the interface constraint and what it reveals. In the real world, you do not always get pixel-level access. You get a text readout. You get an API response. You get a log file. You get a summary. The question has always been what you can accomplish with that constraint. This experiment suggests the answer is quite a lot, including strategic reasoning that the original developers did not anticipate. And that has implications for how we think about deploying AI agents in production environments where the interface is constrained by design.
The developer documented the full process on Hacker News item 47689515. It is worth reading. The description of how the model found the AI exploit and the developer's reaction to realizing what had happened is genuinely fun. That is our show for today. 5 stories, a release that genuinely changes how OpenClaw operates in practice, a coalition that raises as many questions as it answers, a training breakthrough that changes the accessibility math, evidence that AI style might not be the moat the industry thinks it is, and an LLM playing retro games through a text interface. It is a lot.
If you want more, find us at tobionfitness.tech, that is tobionfitnesstech.com, for the podcast feed, show notes, transcripts, and everything else. Subscribe wherever you get your podcasts. We will see you tomorrow.
Stay sharp.
And do not forget to update your models.